there is a mass here, which is the two identical particles, the same mass. So this is the 50 centimeter, and this is the 80 centimeter. Sorry, 80 centimeter. The second mass. You don't care about the mass of the ruler, so the moment of inertia is of discrete particle. What is the moment of inertia of discrete particle? It has a continuous distribution, discrete. The sigma of each. So in this case, what will be? If they are identical masses, will be m times what? No, in this case, it's not L over 2. They gave precisely the number. What is the distance from? So if it's a meter stick. If it's a meter stick, it's right in the middle, right? So we have this in the middle. The rigid body is then mounted so as to rotate freely about a pivot at the 0 mark here on the meter stick. If this body is released from rest in a horizontal position, what is the angular speed of the meter stick as it swings through its lower position? Here and here, the two particles are moving like this. They want to find the angular speed. The angular speed will be the same. It doesn't matter on the radius or the distance. It's the same. So it's rotating. At the beginning, what we have? At the beginning, potential or kinetic? Potential. The potential energy of this with respect to this, what will be? mg L over 2, which is 0.5. So L over 2, mg L over 2, and this 0.80. That's the potential energy, the addition of both. Equal to what on the other side? Identical particle. The summation of the first, m. So m, how many m? We have m times what? What is the distance to the axis of rotation? 0.5 squared. 0.5 squared and plus the second mass times what? 0.80 squared. We have the total moment of inertia times what? 1/2 of the summation of this times what? Omega squared. Can you find omega? The masses cancels out because you will have mass here, and you can figure it out. So this is the question 11. You don't have to care about the stick. Why? Why we don't have to care about the rotation of the stick? Negligible mass. The stick has a negligible mass. We don't care. But if they said the stick is part of that, you need to add the moment of inertia of the stick. If the stick has mass, not in this case. Okay, we finished with that part. We go to angular momentum to close the lecture. But all these questions will be multiple choice. The rod won't be free response, will be multiple choice. Typical question in the rod, find the acceleration at any point, find the velocity, angular velocity of the different type of question, with the rod. The only thing that will change in the rod will be either the axis of rotation or the angle that I want that you find. It can be on the horizontal, which is the easier one, but can be at any angle. Okay, angular momentum. In order to know angular momentum, we need to recall what is linear momentum. And recalling linear momentum, and you can see that in this lecture, the beauty of this lecture, that covered everything. So, everything that we learned before and what we are learning now, put it together. and it's when you understand physics in the whole sense. So, because it's repetitive, you should now start getting. I mean, I know that it's more complicated, but because now you are already used and repetitive, you should know how to approach the problem. And it's a decisive test, remember. Okay, so angular momentum. Angular momentum by definition. Before, let me just recall what is linear momentum. Linear momentum was, we use the letter P, and was the product of mass time velocity was a vector. If we wrote the Newton's second law in terms of linear momentum, sigma F was the change in momentum over delta T. And if the net external force was 0, then Pi was equal to P final. This was the main point in linear momentum. Rotational motion. In rotational motion, we will say that the angular momentum will be, by definition, the general definition is the cross product of R cross NV, which is the linear momentum. The cross product of R cross P. In other words, if an object is moving with momentum, mass time velocity, with respect to any axis, let's say that this is the origin. If we trace a radius vector from here to here, this is R, the distance from the axis or from the origin to the mass, to where the mass is moving, we can find the angular momentum of that particle. Even that is translating, has angular momentum with respect to a certain frame of reference. And what will be the formula to find that? Simple, R cross P. What is R? The distance from here to the mass. What is P? The linear momentum of the particle. So, because we know that cross product is R, P, absolute value, sine theta, the angle between R and P, normal, the same than torque. So, in order to find the direction of the angular momentum, we have to use the right hand again, which is very important. You put R, NV, and this toward the board, we will say that is a negative. If by convention that is negative, we can say that this particle has a negative angular momentum. If it's moving like this, so the angular momentum here will be negative R NV sine theta. If it's moving like this, will be R NV positive. So this is just what will be the angular momentum if the particle is moving with respect to a frame of reference. Now, what will be L in terms of if we go to here, by definition, the net torque has to be related to the angular momentum as well. And what will be? By analogy. I put delta P, but could be derivatives. We are in physics with calculus. dP dt. By analogy, what will be sigma tau? The Newton's second law in terms of angular momentum, not linear momentum. By analogy. This is, the net external force is what? dP over dt. What will be sigma tau? By analogy. The derivative of what? What is P? Linear momentum. This is analogous to tau in rotational motion. F is analogous to tau. P is analogous to what? Angular momentum. So what will be the derivative of what? dl over dt. But what is L? As we know, L is this, so will be the derivative